Hey everyone, so today Juan Esteban will talk about introduction to geometric descent theory.
And thank you, Tony, for inviting me to be about here on the introduction. So today's talk is a little bit longer. I might take 2 hours talk with a small break in the middle after. Okay. So today I'm going to explain a little bit about this work on fan papers and my thesis on geometric descent theory. So maybe let me start with a small motivation. At least for this appears to me and on paper. So motivation. Then we have C over TP. There's a very rough motivation. And at the right, very close field. Marking the field. And E over T. Smooth ridge space. And we call nu the projection of sides from the proétale to the flat side. And let P the OHAT vector bundle over the proétale side. Vector bundle, the sheet of computed functions, the proétale side. So, the motivation is from the following simple question. And basically, is how to compute these commodities. So we have an open value. We like to take, consider this projection to that side. This is orange for the bundle, so apply to the consequence shift. And wonderful to compute subject and maybe put to compute it in terms of linear algebra. Okay, so to give maybe a small partial answer to the question, let's recall the p-adic simple correspondence mathematics. So we recall M. So in this case, well, let me assume that X has good reduction. And maybe I will be very wrong with this and give it actual historical references, just to give an idea of what's going here. And let's say the matrix constructor.
So now X is a scheme, right?
Yeah, maybe it comes from the theoretic fibers of a scheme of construction. Okay. Let me not go to precise. And let's say that so if V is what is called small, which means if I remember the constant property, so that there exists sublattice here like this, such that V plot modulo again is V1 P minus 1, or some constant that one depends on. So the derivative is some pre-module. Then functions associated with this guy. Object that are called the thing of V. And an object theta. So this is its field, its bundle. which is the data of a vector bundle. Bundle of same rank as B. And theta is what I call a Higgs field, which is a map. And always been a map. This guy, or this guy tensor, with tip of differential of X, maybe with a take twist of one. Satisfying the PVC property for the matrix X in here is that 2 times the width equals 0. So this is correspondent, of course. This functor is supposed to be a natural and maybe a tensor with tensor products. And let's say that these correspondence satisfy that the cohomology of this small hat module, which is also called a small general representation in this language, is equal to or isomorphic to a Higgs homology of this corresponding object. So this situation, we can actually compute this projection of shifts in terms of somehow linear algebra, which is basically just a vector bundle and a linear operator. Of course, the difficulty is translated to try to compute this guy.
What does this mean, Higgs cohomology?
It means that because of that property, you can construct a complex like that. But this guy is actually a complex. So it defines a complex because of that
So if B is trivial, then theta is like 0 or something.
If this is trivial, then well, this is also trivial and 0, and in this case you only get a split. Yes. This one is trivial, then the distinction corresponding to the trivial module. In particular, it's not for 0, and we have the projection. This implies that the projection of that is just and I mix this by sorry, we might want here. This is the generality of the Hodge data equation. So in geometrics and theory, what A is and B, so we know restrictions about having good reduction of being the shift to be small. One constructs a Higgs bundle this time Higgs bundle that is attached to B itself. Actually, Higgs bundle of over one. It's not going to be B times omega 1 of Higgs minus 1. It's 0. That is going to be quite related to this the correspondence. This equation we actually have it, and that in general will help us this guy. Okay. So maybe how would this So let me say what of the all this we're going to see. So first, I will try to explain how to construct geometrics and operators or kind of this. And okay, maybe before saying that, we did that. More general. So we are not, I mean, in previous situation of the correspondence is about vector bundles. But in this case, we can actually understand the construction of this N operator constructed for a quite large class of sheets for which we may want to compute projection sets. This is another issue that maybe first we want to discuss about the construction of this map theta B. That maybe will take maybe most part of the code, and in both time at the end, I can explain how to apply this theory to study some properties of the geometrics and operator in the case of Shimura varieties, the way you like the main example we have. Okay. So we want to compute this proétale cohomology, so let's first try to compute it. First, try to compute this thing locally on this. So this means that we can assume also that we have different charts. Given by some curves, then well, we define a couple of objects. So let's just be n be the curves when we have taken p and roots of p. Let me just take infinity, be the perfect curves. Right, so this is perfect space.
Would the indices refer to? D and K or N?
So D is the dimension.
That is number of variables or?
Yeah, the number of variables, sorry. Number of variables. This one is just the roots of D. So let's we have X mapping P. In N, mapping to in N, X infinity, mapping to X infinity. Let me call this group gamma, and let me just take which is just isomorphic group. The copies of CPU1 and the Marlene just at the end and finally, let me just write explicitly the rings of the X because I will need it later. That, so infinity X Here's stuff of infinity, stuff of the end, stuff. Okay. So, this is the perfect vector with this impulse time. So the pullback of T infinity is infinity, is just an entire map of the perfect vector, so by adding probability. So also we know that this X infinity is also perfect. So this one, the perfectly covered. The vanishment. Of coherent cohomology. Proétale perfect spaces. We can actually compute this projection of V as the cohomology by gamma, maybe actually let me write as the proétale cohomology of V1X, we will represents as the projection as the cohomology by gamma of V evaluated at infinity. Right? So this is just something that right from phases. So now, in order to, let's say, make appear this operator, we'll try to compute this cohomology. We can use the theory of local analytic representation. In particular, this theory of, we would say, solid local analytic representation told me how to compute group cohomology of p-adic groups, at least in characteristic 0. So in this case, this group cohomology, let me call this thing by W, so I don't want to write time. Cohomology of this object, I can do it in 3 different steps. So first, I can first try to compute the local analytic vector for the action of gamma, and we get the right local analytic vector for the action of gamma. Then, so now I have a local analytic representation. I can compute the algebra cohomology. Once I compute the algebra cohomology of this representation, I get with a smooth representation of gamma. So at the end, I can compute the smooth cohomology of this smooth representation of gamma. So this is just like 3 steps that is out of cohomology in terms of these theoretical representations. And like this quality will start motivating the separate nodes of the sandbank in the but this when we have coordinates. So this quality translates are probably into steps.
Can you explain what this derived with the analytic thing?
I think I will explain it.
Are you going to use it?
Yeah, I'm just using that. I mean, let me discuss this locality later, and maybe just give a formula for what it is. Okay. So if you have W.
What is your first function? So you derive smooth vectors?
Yes. So you have a smooth representation. This defines a category. And in this category of smooth representation, you take cohomology.
Which category? So with R gamma, gamma, so on. This is already smooth. And now in which category you derive a smooth?
The direct category of representations, which is not the same as is different from the direct category of continuous representations. It's just this difference. So this cohomology is taken in the direct category of the smooth representations, maybe solid smooth representations.
your dot smooth papers when we did the
Okay.
In particular, when you take cohomology groups, this is just taking the cohomology groups of the algebra cohomology and take smooth vectors on the nose, because the smooth vectors in characteristic, it's taking the invariance of a smooth representation in characteristic zero is exact. So it's basically
what confuses me, why we derive things this inverses.
I don't know, just because it's a complex. This is just a
Yeah.
this may be a complex, just to write down a computation. No, nothing. So like I said, so we have this stretch. Step 1, step 2, step 2, and step 3. So the first one is to understand what this guy is equal to. Let me just write very quickly what this is. How to compute this guy. So basically, you're looking for elements in W for which the orbit map is local analytic. So cohomologically, you can write on this by taking this product, where this one is the left regular action. And then take the group cohomology of this guy. Right? So this one is just measuring those elements in W which whose orbit map is local analytic. Let's say he's done in a way that is compatible with Rust here. So I can mention this thing for later. Let me just do this. So the first thing is to compute this guy. Once we have computed this guy, then we need to understand the action of the algebra of gamma.
So gamma is equal to G.
So gamma is equal to G, yes. Which at the end, the action of the algebra is going to be the separator. And finally, we need to understand this smooth homology of gamma, which, well, I could say is not varied, just something exact in the abelian category. And at the end, it amounts just to the descent this. So the more involved steps are the one and the second, or mostly the first. This one is just, again, just some meta descent that we are going to more or less ignore. It's not the hardest part of these stations. So, let's just follow the steps. So first, let me discard the step 1. So for this, step 1, I need to briefly recall at least in this context, what is this theory of chain theories? Basically, chain theory is used to compute different. Can be summarized in this way. Okay, so I have the rings of the data. So,
what is this in parentheses in step 3? All yes.
This is a
Yeah, and the other words.
the descent. Sorry, this is maybe you could say just descent. So I'm actually finite descent. So this picture is easier than this. Okay.
Was gamma?
This gamma.
Yeah.
This gamma is the group, the gamma group. Is perfect with
Okay, fundamental group.
yes, not the group.
And this one, I mean, because X was algebraic field, so it doesn't really play a role, right?
It's not very close field, so it's an actual galaxy.
But what is this one? Is it P1D? But
Well, I mean, the one is just to keep track, even if it not appears the galaxy, but this So since we are over C algebraically close, it doesn't matter, but just like to write it. Just need to say that what appears naturally at p roots of the one unit. Just so. Okay. So the traces, right? So we can take these traces over the enters, or the detours, and n from this guy to this guy. And we can normalize so just using the cardinality of the calculation. So it's going to be n minus n, and we multiply by this. So this guy basically the projection. Onto the basis onto the free elements. E A over P to the S, where S where A is an integral, and S is smaller than X. Right? So these normalized traces for the torus are just using the natural basis that you get from these roots of T. It's projecting onto the monomials that have no more than Pn roots in of T. Just projecting. Actually, at the limit, and goes to infinity, they will converge. Well, that might be variant. Projection. From here to the end of the perfectoid curves towards these n-level curves here. It's just again just projecting into these monomials that appear on the right. And moreover, so let me
Is A in N or in Z?
n is in n.
A.
Right. So turns out that traces can be actually too bad if the rings attached to those recipient here. Basically, since it's in this perfectoid that lots of analysis in Peter's radical theory paper, the traces standard for n big enough, the traces of this ring A infinity an that satisfy the following properties. So the first one is that one can actually control the norm of this trace map. So, yeah, for epsilon 0 so exists large enough such that for n bigger than this one, trace of infinity plus is inside p minus epsilon. So in this case, of course, epsilon can be certain as 0 because n is quite great. In general, we may need to take the trace of a small epsilon that can be chosen small enough as long as n is large enough. So this is just saying that you have control in the trace space. The second property, let me just assume in this case that we are in the one-dimensional case, just to make it simple to state, is that if we denote by dn the kernel of the trace, in particular, since it's a projection, we know that infinity is dn plus an. Then, for all epsilon bigger than 0, there are two constants. One bigger than m big enough, such that for all n bigger than n, and the gamma m generator, we have that one minus gamma m acts here invertibly, and actually we can bound its inverse. So its inverse sends dn plus, if you show the intersection with the plus, to p minus epsilon of dn. Okay, so what does that mean? Well, let's maybe in the example. So in the case of these equal trajectories, we have these rings C P plus minus 1 to infinity, projecting the trace C P plus minus 1 over PCN. And actually, well, of course, the first bound is just trivial because already bounded was nothing bounded, so it's okay. And the second one is basically saying that if you take a gamma generator of the Galois group and you apply it to P1 over P to the n, which is equal to Pn plus of unit minus 1 times maybe 1 over this P1 over P to the n. In particular, is if n is large enough, this constant will get non-zero, so and actually very close to 1, which will say that in the kernel of this map, which basically consists of all the monomials which are denominator bigger than n, this guy is going to be invertible, and the bound of the inverse will only depends on this kind. So this is just an axiomatic way to reflect this computation that is quite easy in the case of curves. So maybe in the values and works. What we have first is that maybe let me think so. Let me copy this one and this two. So this means always annotate after couple of actions that appears in the fork of Herlian Holmes.
Yes, okay, so you give an example, but beforehand you talked about dn. So does this T one of the Pn lie in the kernel of the trace map?
No, I mean, of course. This is, okay, maybe I should put another n. Maybe if I take an n, we have then n minus n.
And less or equal to n. Or no?
Yeah. I'll have this for anyone.
I see. So this would be like, you have zeros in the diagonal, right?
Yes. Up to the step n, and then you get this constant here. Okay. Basically, this action, the one, says that there exist traces, there are traces. There are 10 traces are controlled. So we can control the bound of these 10 traces. And the second action is that for the kernel, we trace the group cohomology gamma trivial. And let's say that draws some explicit bounded, explicitly bounded someone. Okay, so this is basically a very different way to apply this. So now let me go to the actual statement of this vision process.
So that would be CST2.
Yes. Now maybe we call it the position. For this, I may want to take a position. So once you have this tools, basically the state traces, and you can complete well, and this bound for the kernel, for the cohomology of the kernel of the state traces, which actually means a specific homotopy given by the inverse of this 1 minus gamma.
Are you computing the group cohomology via coastal complex? Is that?
Yes. And say, let me make it slightly clearer. So this is on the homotopy. Yeah. And that's why I use this bound for the 1 minus gamma. Okay, so there is the superposition. Remember the fullness. And maybe put also okay. That will be the gamma equivalent. Vector bundle. Vector bundle, so this way.
Sorry, just still understanding. So group homology of like gamma and or really mean the original gamma.
I mean maybe some other gamma m.
Okay.
Maybe yes. In this theory, maybe I should say that according to this theory, you allow usually to go as deep into as you need in order to make a cover the computations. You're allowed to change the gamma based on gamma s, with the n's based on larger thing. Because, well, let's say that the spirit of this theory is from like asymptotic kind of properties, which are reflected in these actions.
But we characteristic zero anyway, so if gamma m vanishes and gamma O also that.
Indeed. Yes. Okay. So let this abnormal equivariance value that. Then there is an n which is big enough, and a gamma equivariant vector bundle Vn living over An. Of course, I mean everything is semi-linear action here, such that with V equal to Vn tensor An infinity as representation, such that the first property you can pick up from these guys is that this Vn is local analytic, actually analytic, gamma n analytic. So it's going to be analytic for the action of gamma n. This is n is big enough. Maybe some smaller n, I don't know. And so we model a couple of asymptotic behavior. And if Bn is equal to extension of scalars with Am or n bigger than n, then let's say that these two systems and B are just combine each other, so they are isomorphic as in system here. Maybe you can arrange that actually the gamma analytic represents this size, which will allow you trickiness, but basically what is important is that the system given by the base change of this kind of the completion over Am to any other parallel Am is the same as the analytic vectors. These ones are not yet derived, at least not yet. Just the usual analytic vector representation as this system here. In particular, let me just do this. And the second one, which is part of the analysis behind, is that if we pick up a basis of B, such that the plus, which is just the lattice generated by the VI, that is gamma stable. Again, for any choosable basis, we can find gamma small enough that this actually happens. And all C bigger than 0, so any constant, here, there exists of M big enough, and the other prime basis of Bm such that Vi, we are unique basis of Bm, such that Vi is equivalent to Vi prime modulo C minus epsilon. Sorry. So for all C bigger than 0, no choice about K. So basically, this means that not just we can decomplete this representation, but whenever we pick a basis, we can always approximate this basis by analytic vectors as close as we want. Maybe once we allow a smaller radius of analyticity, but we can approximate the basis of the representation basically uniquely in a field of sense as much as we want by analytic vectors. So this saying that basically the analytic vectors actually exhaust in a dense way the representation. So this is like the proposition that appears in the box. Let me boil down a slightly stronger statement that already follows from this proposition.
So my first is pick C bigger than 0, and then it's for all M. So that's
Sorry?
It's parsing the quantifiers.
You pick, like, you pick zero, there is some radius of analyticity, big enough. I mean, radius is more enough.
Okay, and then what? And
Unique basis that is enough, it's close enough to be valid. Let's say that maybe this thing may depend on.
Hard to understand what is the condition and what is the statement.
so that there exists C bigger here.
Okay, sorry. You have a basis,
Okay.
for which let me try to write in a slightly different. You have this basis.
And B plus is the definition of B plus, or
Sorry?
is the definition of B plus?
It's just the lattice generated by these spaces is not enough. Which is, let me pretend that sorry. Let's say bigger than 0 such that since BI modulo to the C are gamma invariants. Again, modulo taking gamma smaller, I can guarantee this property. It's just saying that modulo to the C, this guy is just a small representation. Then
Wait, so is BI is like small? I mean,
relative to the action of gamma. Whenever I take
what
BIs,
is BI? Because this is represent this characteristic 0, I thought.
yes, but I told you that this lattice is gamma state.
Okay, but what is BI?
It's a basis of this lattice as well. This BI is just a basis of B.
I see, so it's a small BI.
Yeah, I don't know that. Yes, small.
Okay.
Each of them is fixed by gamma.
Yes, each one is fixed by gamma. Then there exists some big M, or maybe then for all epsilon bigger than 0, there exists some M big enough, and you need basis one of these epsilon is more enough. If I prime of which are in CM, but also which are bounded, such that BI is congruent with BI prime modulo EC minus epsilon. So, if you forward. So again, try to say what this means. It means that whenever you pick a basis of P, whose reduction modulus 1 power of P is fixed by gamma, okay, a subgroup of gamma. Then, once you have these properties, you can always approximate this basis by some analytic basis. And the radius of analyticity, I mean, you can approximate it as small as 1, depending on, as close as the action is trivial, depending on action. Maybe that's sorry. Maybe, okay. Let's say that you can approximate it.
Maybe some action condition on BI prime. Gamma, I mean, should be like gamma invariant or something like this.
Because of this, it's going to be a gamma invariant that is modulus of power. Because of this condition. So, for example,
well, what happens if I replace BI prime? I add P times C or something.
BI prime.
Why is this base unique? I mean,
these are computations that appears. I mean, the uniqueness is made because of this kind of constant of this approximation. And this is telling you that, like, once you fix this radius of analyticity somehow, like the function is determined by these ones. But let's say that at least the uniqueness comes from the from a kind of from the computations of the theorem. I see, so you cannot say there's something more concrete.
But I kind of agree with Vitas. It doesn't feel like there's enough rigidity. Like, why can't you just perturb?
An a-linear change of basis, right? Okay, that wouldn't affect any of the.
Yeah,
That
you
would
could.
affect.
Okay. This VM, or at least as
Are they fixed by gamma? I mean, if you were fixed by gamma, for example.
I mean, the modular thing they are fixed gamma, but not themselves.
Why would that be enough then? Couldn't you just add like very large multiple or multiple of p to the very large power? It would still be a basis. Yeah, add like p to the billion times epsilon or something, and then like it's still a basis and it's still the same on p to the.
Let's erase this. Yeah. It kind of I'll do this properly. The next window. Let me after break just check what the uniqueness was and that's it.
But in our previous example, I mean, like when we started, the action of gamma on this VK, so doesn't it factor for finite quotients? If this vector bundle comes from X, this is like a tau cover.
Once again, good.
So I'm trying to understand this condition. The n is gamma n analytic.
Yes.
But I mean, aren't these in our setup, aren't they like smooth representations?
No, they're not smooth. They're not going to. I mean, when you take p-adic cohomology, it's going to be smooth, but not with the completion. What was smooth was the p-adic cohomology of these local analytic guys. But this one is just the local analytic guys.
But it's not. So what we start on a bundle of X, and then we this Vn is then obtained by weight shading. It's like a finite tau cover.
This one is going to be a bundle over Xn, yes, but the action of gamma may not be smooth.
It's not going to factor for
Still, you can descend it to something finite rank, but still, if the action were smooth, then the Sen operator would be 0, and you can actually come from a coherent bundle like dumpsters. If you know that you can only complete up to a certain level, and the action is not necessarily. Let's say that the action, I'm going to spoil a little bit. The action may not be smooth, but this is important because of this local interaction, you will be able to look at the Sen operators. And the usual simple correspondence, you use these kind of Sen operators to de-twist the shift and to encode the Galo action in this Higgs band. So it's kind of an additional process you need to make in order to recover a shift first, and to recall the action of gamma on these BNs using this Higgs band.
So an example would be if I take this example, so this would be just my VK would be just C brackets T plus minus 1 B to the.
Yes, and in this case, the action is true.
In this case, the action is.
It's just smooth.
Right. So this is what maybe was confusing.
Yes, yeah, no, in this
So
case.
can you give like another example?
It would be twisted by the character.
Or some local entity type.
Of set P of 1, for instance.
Okay, sorry.
Right.
Okay.
We got this part. So, saying a corollary of this, following is actually we can compute the derived local analytic vectors of P, and these are actually just in degree 0. It means and as I call this Yeah. This is just the colimit of all the Bns here. So how to deduce that from these equations? Well, right. We can write these at the extent of Bn plus Bn of An of Bn, right? So we know that Bn, so the limit, we also have the B because the colimit of the Bn plus the colimit of the tensor. So since these guys are analytic, then it's enough to prove this system. Again, that's okay. Yeah. When you take gamma n, and you can allow this to be variable analytic errors. Is in the zero. Right? You only need to prove that the arrows will become zero in this system. And only the idea, let's say in the case of t equal to 1, I told you what this object is. This object is just the cohomology. So this thing is group. Group cohomology of this tensor. When you also tensor by the analytic vectors of gamma n, with the left progression. And now you use a couple of equal to 0. And use the following. The first one is that we call that 1 minus gamma is invertible. On the end, by hypothesis. And the second one is that actually 1 minus gamma is divisible by a control of E on the lattices of Bn tensor QP Cn from n. Basically, this is telling you that obeying an analytic representation, broadly speaking, means that the augmentation ideal of the Iwasawa algebra is divisible by a part of P. This can be seen when you look at, let's say, a lattice in here, you reduce modulo P. You basically only get the reduction of a polynomial ring. And the action of gamma in this polynomial ring factors through a Planet quotient. So this will imply that actually, maybe for another gamma, 1 minus this guy is actually divisible by P in a lattice of analytic representations. And this actually spreads out through all the analytic representations. So, for example, if you take the analytic constants of gamma P and gamma Joseph P, so this is just PP series ring. And well, And you can take the left regular action is just mapping T to T plus A. And for A in C times a T, this action on T of T, right? Which is just the relation modulo P of a lattice here. So being analytic basically means I imported the implementation analytic for power of P. And the point is that now, because of these properties, 1 and 2 will imply that this action of 1 minus gamma on this tensor is vertical. At least want to adjust the constants n and m large enough. It would be vertical after. The n and the n. Or maybe Cn, right, like this one is divisible by p, this is invertible, and you can manage to construct explicit inverse. So, in the case of one dimension, this guy is invertible, you know that the cohomology is 0, and you basically want all dimensions to do kind of the same argument. Using some.
And did you, I mean, you have this d equal 1, or so are you saying you're reducing this to this case?
But basically, at the level of computations, not geometrically, but the level of computations, you reduce the one dimensional situation. Yes, you just, I mean, since the action of the other components with each other, you basically only need to deal with it. And maybe it's a good time to break, just to say that maybe I'm not going to give a sketch of these things of the proposition that involve this decomposition. Maybe let me just mention that, well, maybe from the practice, let me mention ingredient hero is the idea. So, yes. Okay. Is that again, well, you have an end rank representation, so this one is basically the same as giving a cycle to GRN of infinity, right? Just having an n rank representation in this cycle, such that because of these conditions on the variables on the basis, you know that this one is trivial modulo this power of this cocycle, which depends on the basis that you start with, is trivial modulo this. Basically, at the end, again, doing basically for one variable and for two variables, you just have four computations. Then you write sigma of gamma at 1 plus n, but n is just a trivial modulo p to the c, and then you traces. Right. This one at 1 plus the trace at some big enough level plus one trace. And this one now belongs to again, I guess you write on the end you have fun. And then if you use this second axiom involving the vanishing of this cohomology of the kernel, so this one belongs to the kernel. You find that a matrix is congruent to 1 plus modulo maybe p similar sets or something like this. Such that cycle becomes congruent one modulo p plus delta for some delta depending tensor. Epsilons of p functions. Right, so this delta is dependent on the epsilons in this statement, but depends on the epsilons in the other. And then, since this one is kind of independent statement, this one maybe is also kind of delta or something like this. The epsilon is also fixed. But then iterating this process, you can build up a sequence of matrices E, which are going to, let's say, modify the microcycle. The product. Guys, in order to satisfy.
This thing, if you look at the thing, it looks like it takes values in AN, but it could be taking values in the matrix range, right?
This one belongs to the other. Yeah.
I mean, so you're right, sigma gamma is equal to 1 plus n, and then it, so this is the matrix, right?
Yeah, just
And then you have equality, and now all the elements seem to lie in AN. I mean, you write in AN or
no, I mean, fourth. Sorry.
1 minus trace
In the second line.
scale.
And this here.
Yeah. Yeah, that's
yeah,
okay.
1 plus trace NM. So this is, you write,
Yeah, those are scale.
Yeah, just projected in the trace and then the kernel of the trace.
what happens then in the next line? What is 1 minus trace N?
This is just the other projection. The projection is the kernel. I mean, just the kernel of the trace. You project it to the other trace. I mean, I just have ends. And identity minus.
Okay, that's not.
Too many ones. So this is only the idea. You start approximating this using the traces, and you end up computing. I mean, for this, you use these actions that allow you to take the output. Okay, so any visuals that will take a break of. Let's say, for example, for Banach representations, Banach infinity Banach invariant modules with basis. I such that there exists some n bigger than 0, where the action of gamma n in these bases. So basically, it's enough to ask. Let's say that in the Banach rank situation, we can do this because there are infinitely many vectors. In the Banach situation, we need to guarantee that we have triviality of the basis, modular power of p for uniformly all these guys at the same time. And actually, let's say that maybe an alpha. That we have some gamma plus p plus p, such that there exists an n and c bigger than 0 with d plus modulo p to the c to be some base change like that. Let's say where gamma n acts here. Actually, what should only matters in these kind of computations, if that maybe the argument is that again, that this representation V is not far from being a locality representation, in the sense that at least you can find kind of lattices whose reduction modulus in form of P already arise from something that is trivial, which is this some representation which is already trivial.
What is the difference between the first thing you wrote and the second thing you wrote? The one, right, the first one is,
This one,
I know this is enough, and the second one is, this is enough. What is the
I hope
difference?
this is enough.
Hmm?
I hope this.
No, what is the difference between this condition and the previous?
Let's say that we can make this statement also right.
Oh, yeah.
For example, that will be yes. So this guy is one of the connected.
Is that classically P complete or super collapse?
Right. Yes. Something like this. Hopefully, it's not guaranteed that we can actually be completed. But maybe just to write down what I see here, I mean that this should imply that when you take your analytic vectors and you make change, again, look at the most of the nice. Maybe that we can also say something about the local analytic vector in terms of its approximation modulo power. Okay. Now that we have understood the step one of this decomposition process, let's go to the step two of this Lie algebra action. Now, two kind of paragraphs. So this is easier. So we have B for infinity with an action of gamma. And now we can look at the array, the locality vector, which is the co-limit of this decomposition. Right. So this is a module over maybe, let's say, the first example of theory, you take a trivial representation. Then the Vn is just the An. And the locality vectors of this guy is the co-limit of these guys, which is the smooth vector. In this particular case, we have that Lie algebra gamma acts of the general spectrum act from ELA by, let's say, infinitesimal linear mass. Just so it extends to infinity linear mass. This map what we call the xenophoid. Maybe it was useful to write down the handle because they are joint of this. Right. So why is this useful? Maybe our proposition allows to it helps to explain what this also the dilemma. So let's be we're finishing the gamma interpretation and again, what I'm going to say also applies in at least for Planck representations. I define the property about before. Suppose that the cohomologies this model. I should mention that the Sen operator also satisfies the property that it can hit field, basically because we just did the algebra gamma, and gamma is equal to group, for instance. Maybe we need to suppose that these guys are projective over infinity, just to guarantee then the cohomology and the computers the cohomology is operator, and then taking that variance by G. Okay. The hypothesis of this guy being the objective, we imply that we can apply the Computation theory, let's say. It means that the local analytic vectors of this guy we can give zero. Right, because it's a vector bundle, so we can apply just what we did for vector bundles and know that this guy is integrable. And once you have this, well, you have the canonical filtration of this complex by this field with cohomology groups, especially these guys, and taking local analytic vectors is in the cohomology groups is just integrable zero, then when you take the cohomology of local analytic vectors, this guy, because of the property, this is just this guy here. So gamma acts smooth. Guy, one gets that the cohomology gamma G is just the cohomology gamma of these local analytic vectors. Which actually is just the cohomology of theta basically equality like this. So saying that if you are in good shape and you know at least all the cohomology what the Sen operator looks like, then you can actually compute and use them to compute group cohomology, which is what the motivation at the beginning of the book.
And the Sen cohomology is the algebra.
The group cohomology on D can be computed in the Sen operator, and then you just invariance of the cohomology of the Sen operator. Right? Our Sen operator, you have a complex in the Higgs field. And this is telling you that invariance of this cohomology of the Higgs field is the same as the group cohomology of D. So the idea is that this one is the goes the hard part to compute, and then you just take invariance as long as you know all these things. yeah, basically the invariance of the same cohomology is good. Yes, the invariance of the same cohomology. Okay. So now that everything starts with this torso given by perfect torus. So let us explain what happened for more general torus. And let's say that the situation of homogeneous torso follows the work of file. All what was before already more or less in the work of Project Congress, at least most of the technical part, the only additions. This local analytic business, but basically everything already appears in Project Congress. So, the local our setting is over C a smooth variety that gives you a compact p-adic group. And let us take still over X and G torso. G torso in the proétale topology. Just to first we look how we globalize the assume that these are from origin context. We can form a diagram where infinity is by the coordinate is gamma, it's by G, it's by the product here. So gamma G and G. Where is this equation? Basically, well, we want to know what happens. So the question is, what happens for Sen operators? License from zero perspectives. Okay. This in the properties remark is that given V or W maybe open bundle, actually the functor, let's say under this functor, this guy satisfies Leibniz or thousand products. In other words, you have theta of a tensor of two sheets. By construction, this you take complete along the direction gamma, and then you took the algebra cohomology. So you took the action of the algebra. The action of the algebra actually satisfies these properties, and this is just how it is. Yes. Okay. Next mark. 1. 2. Is that it? Let me. Yeah, the right or finite dimensional. Maybe you have something more. Yeah, local analytic. representation of G. Maybe let me just depend on this and LB representation. Okay, correct?
What is LB?
LB, coordinate of
I see, yeah, approach.
yeah, topological. Then we can embed V inside of the yard. This is a complete product. Solid tensor product. So this one has a trigger action. And this one has the right trigger action. This map is just the orbital. So it implies that the Zen operators, so the Zen operator attached to the local system. Yes. Then the point outside. Then because the path is rejected, the Zen operator is right on the depends the Zen operator associated to the continuous to the locality functions. I'll put the right program. Because you can embed the V into that, you send the scalars, then the Zen operator is nodal the construction, and the only thing that will happen here. And also this map is not very enough. Then what can we deduce from first and second remark? That well, the Zen operator, recall that which is the part from the algebra of gamma towards one. Well, the first one says that actually, well, since this one is an algebra, the Zen operator will act like derivations in this, right? We can offer linear derivations of this algebra, but regular action. And since it's acting on the right, the group, then multiplication on the left is actually an automorphism of this cohomology here. So it's nothing to do with the way you actually embed it into the as a shift the product. So this is also but the relations of the space with the G equivalent of the red function is nothing but in the algebra. Making and implement this algebra. So conclusion, we get proposition. The previous situation. For being a local analytic, we have a diagram like this. We have the action with the operators on B, control hat. This, well, we have a map. The algebra going for the algebra, let me just call it Zen, that only depends on the torso. The algebra. Then we have here just the derivations along the map of G tensor P towards P.
Yeah.
No.
I mean, symbol below, straight below.
This?
Yeah.
Supposed to be about this.
The DL.
Oh, well, yeah.
The algebra. So in the case we have torsors, we actually can say something about the action of the single operators in modules arising from this representation is that all they come from just morphism over the Lie algebra and then imposing the derivation, not from derivations. Okay. Now that we understood locally how the same operator works with torsors, next the question is well, how to globalize this proposition. And this is what follows the theorem. Fine. So the maths. And still the Lie algebra of gamma, the local mass towards G globalize. To map come from what is this guy, the tiniest case. Okay, so well, this is if I correctly is kind of the data of G Higgs field, I think. Maybe knowing a little bit more. Maybe knowing that the second words of this one is point is that this map of the constant locally actually glue to a map of the tiny space. So let me try to explain how this happens. So it's enough to prove. If we take an arbitrary over, we take vector bundle, then well, and we have two parts, C1 and C2, with groups gamma 1 and gamma 2. Then so we have an isomorphism from coordinates. E, EI, 1, EI, or 1 means. This one, the right is just 1 by G. So C by G. D by second coordinate G. Alpha. The map given by the previous proposition. Right? Whenever we have a torsor, we have a map of the Lie algebra of one of the torus coordinates into the other torsor. So this map arises from this proposition. And let me say that I mean this one is I You can get numerical coordinates and you can sum one ice. Right, just writing down what explicitly I need to prove.
I'm trying to ask, so like, what does this have to do with the other sin operator that would define for vector bundles? Like the sen x tilde. Okay, so there was before for vector bundles, there was
Yeah.
like
Yeah.
bundles.
There was vector bundle, so okay. You're right. Let me bundle. Let me just write down this stuff. Okay, maybe not. Let me just write this, and then explain how the vector bundle plays a role.
Still, even in the stuff before, so there was like, before there was a sen operator for a vector bundle, now there's like a thingy, the representation of G, like.
Yes, so, right. So in this case, I mean, the case when it's still there, it takes a more complete something. Maybe two different. So in the case when G is equal to 1 So first, you try to prove this independence just at the level of the historic coordinates, and then somehow you can extract the independence of an arbitrary torsion G from this case.
So is it like in relation to the stuff from before? Are we trying to talk about like G equivariant vector bundles or?
I mean, like I said before, whenever you have a G representation, you can construct a vector. Well, you can look at the same operator of the G representation, the extension of Camargo hats, and the proposition says that this is kind of more or less independent of V, and only depends on a map from the Lie algebra to the Lie algebra. The sign operator can actually build that from this map using the natural derivations of G. So what I'm trying to do now to explain is that this map from the Lie algebra of these gammas, which are local, to the Lie algebra of G, which is something global, actually glue to a map of the tangent space to the Lie algebra.
How come this theta phi doesn't have a Higgs bundle?
This to that?
It's not a Higgs bundle, yeah.
I mean, okay, this should be the same opinion. Like, can we tell me nothing? The same operator, which are going to the Higgs bundle.
Oh, okay.
So, okay.
Still, I mean, the Higgs was like you twisted by the differentials on X, whereas now you're twisting by.
Yeah, the differential of X. The point is that this guy can be identified, tensor with the tangent space of X. And this is similar here. Maybe let me emphasize such that for the Lie algebra maybe such that this extends to time space 50/1 and go to fill that the Lie algebra and B control hat. You can differentiate B control hat. And then this one, you're going to define an adjoint to this one. What do we have? I mean that this one was there in the differentials.
Hopefully we recover a biggest payoff on the same. What we will recover the biggest payoff.
I mean, this map It's just a joint to a map from B towards B tensor the differentials, which is the yeah. Sorry. So
Maybe that should be stand V.
right. This should be something.
So what is X here, like? Lie also, the tangent space of X is the Lie of gamma, or gamma is some specific thing.
Yes, that's the serious part of the. Let's okay. Let me finish putting the thing here,
Okay.
and then I say why this. I think what the E of gamma related to time space, maybe all these things are going to be related.
Yeah, two groups, gamma 1 and gamma 2, so what?
Yes, in this case, they have this.
But, I mean, is it gamma 2 like G, or what's the relation? Or, I mean,
No, this one are just coming from two different toric coordinates, so kind of disjoint each other.
okay, this psi 1 and psi 2.
Yeah, side one and side two.
And in your formula, in the denominators, the TI and TJs have also the superscripts 1 and 2.
Sorry?
The TI in the formula in the denominator.
Yes.
And on the other.
Thank you. So I'll just write down what here. So this guy, it was somewhat there, or seems to be just everything here compute. And let's say that the reason when we expect such a kind of computation is because of the following. Let's say, position. Short second. In the summary of these cases. Paper. It basically says that whenever we have H1 front out of O hat is equal to the differential, so H divided by -1. Maybe we are in characteristic close algebraically close fields, so we know the case, in fact the come right. And this guy, when you have coordinates, it can be computed as H1 of gamma 1 of, let's say, infinity first completion, but using in theory, this is just the same as H1 of gamma of A. And you can do the same in the other part. So the way you compute these things are yeah, let's say that the way you end up identifying there is a precise map sending these guys theta i's to the dual of these guys here. And this pairing, at least you arise from something which is a quadratic field, for instance, is an explicit computation that came up using the plugging stage first. So at least in this case, when you come from something p-adic, you can motivate in this way, and in this more general geometric equation, to use this proposition instead, and this equality of cocycles to make this appear.
Is the content of the proposition that you can describe the map that way?
The content of the position is that you can actually compute what alpha is. You can compute what alpha is in terms of base change of the tangent space, which is just the adjoint of the base change of the cotangent space. I think that is the position. So, right. So this position, which is again maybe say that to prove the position, you use such a property here that you can compute it for like cohomology of pattern that is the Coulombic complex for the demand, and that you can describe this one in terms of cocycles. So, and actually, you know what the cocycles go. Here is like a cocycle, sigma 1 of I, that sends a basis. Of I here equals delta ij, and this one you will map it to the I think it's minus dt. You will map to minus dt I 1. Yeah. And similarly for the other one. So you have cycles, and you know what the cycles are mapped in this base. So this will tell you that is the H1 of this infinity 1, 2, that is just the functions of this of the product. So this one is the same as what cocycles here, about zero. Like the way to compute for the cohomology. Then in here, the cycle gamma I 1 minus j. The other one, I did the other one. No, it's this one. This is 0. And basically using this this will give elements I in this ring, which actually are going to be local analytic. Such that local analytic. Well, it represents this cocycle, so concretely, it becomes that when you have gamma I 1 dj minus dj, this is just you can make it minus delta ij, and then you can make the other appear 1 gamma 2 I dj minus dj. This is going to be a CGI.
What is this formula you find also in the formula that you were done for sigma R1?
Sorry? What this formula
On the blackboard version one.
This one?
Yeah, gamma J1 goes to delta RJ.
Because gamma is active trivially on A, so since gamma is basically free, and able to send the basis.
And the first inequality that gamma from A infinity, this is used very previous as well? Or
Yeah, it's can compute the completion just taking some analytic vectors. So once you have these vectors here, then basically you know that the action of the Lie algebra here is going to be kind of important for the first factor. So it's going to give you like the trigger, the standard representation, while in the second factor it's going to act via these constants. And let's say that from this you hook up a representation that gives you this base change here. Just using the Which number? Let's say that is also painful for the action of the third one, P of gamma 1, because it's just one delta. So it's painful for the action of the third for the first one. So this proves the gluing of the Zen operators to the case when gamma is another coordinates, but then the general case just deduce from this corollary. Now I respect W actually of our vector bundle. Then the algebra of gamma 1 that maps to any morphisms. To all linear endomorphisms W, the other person operator in the solid multiplications. And 1. So after this, applying this map alpha, that was the way. Make this thing commute. And the reason is that, say that proof. So first, we can decomplete this guy using the analytic vectors. And the action of the Zen operator. So the action of 0, gamma 2, only depends on the map given by this guy, right? Because anything else can be just written here and then the guy inside some local analytic vectors of the gamma 1 and basically local analytic vectors can be embedded into this one. So the action of P2 only depends on this map and already compute what the action of this is. So this implies the gluing for the shifts. And let's say that once you have the gluing for an arbitrary Johann module, then you reduce the gluing for the torso just applying to this map gluing for torsos. By looking carefully. This will reduce the case when you have an arbitrary of the bottom, and because of this completion here, in the previous position, you actually know that you can do this. So, time is over. So, yeah, maybe we just demonstrate. Thank you. Questions?
Yes. Like all resolved, yes, it's the power.
Oh, sorry.
What you said is like if I am doing this, the gamma is somewhat.
Yes.
Global one.
Yes. I mean that this real gamma, so in this case, it's endomorphism, but it means the purpose can be glued to the time space. Like one. Yes. So this one can be glued because of its base change quickly that we can compute. The previous cocycles. This one is going to glue to come out from a time space. It's the algebra.
So is the application Shimura varieties, is it the vanishing above the middle degree?
For instance, this is the first application for this function. So in the case of Shimura varieties, you can actually compute this map. So before to send it to Hippie. For Shimura varieties. This Taloca system, because of the human liver, has touch state weights between -1 and 1. And this map in time space this right. It's actually the one where it is. So this implies that this guy is actually the first piece of the Hodge state iteration of this one. So you can compute it quite easily.
What state weight is it to be with respect to mathematics?
Yes, I mean, yes. In the case of this Shimura variety, you actually come from some p-adic field. So now you can keep track of the take weights that I wrote. And this one has Hodge state weight 1, so in particular only maps to the first quantities. But it turns out that it's actually equal to the first quantities. Maybe modulo equal to the first quantities here. You can compute it and see.
Thank Juan.